So first of all, I wish to open with this picture that I sent you the last time. Have you seen in your my previous email?
Yes, bro.
So this image that seems like snowing somewhere here, but this is a very so the image that is so impressive because this image was taken by a space aircraft, so by the Rosetta space mission that goes close to a comet. And so this is the end of the mission. At the end of the mission, the probe land and the switch off on the surface of the comet. So what we are seeing now is the surface of the comet, and the sparks that seems snow. They are it is the material that is released by the comet. So when the comet passes close to the sun, you have like the evaporation of material and the removal of some parts. On the back, you can see there it looks like a spark, a big spark. That's also here on the background. You see the bigger dots are the stars that are visible on the background. So it's very impressive image that we can get from this comet. This mission was very important for the study of the comet because inside of this spacecraft there was a gas chromatograph attached to the mass spectrum. So we are able to make some detection of the components of the comet. It is mainly water, so like snow. But so this comet, I think, is some kilometers in length. So since it is a big object, but not so big for the gravitational force. So this like snow is not compact and it is very soft. So the total, the total density of this is less than half of the density of the normal snow because it's not compacted. And so in the analysis of this showed some components that are very well known that are present on the icy dust that we can observe in the other objects of the solar system. So we confirm that comets can be shattered for carrying these compounds everywhere around the solar system because the comet has a part that is close to the sun when it evaporates, and the other part of the life of the comet is spent at the border of the solar system, in which it can collect some icy particles and other molecules that are present into the outer part of the solar system. So they are like carriers of organic molecules. At the moment, we know on the surface of the comet, we have only simple compounds for sure that they can be combined. So when you hit this higher temperature, you can have the formation of amino acids and all the other compounds that are the basic components of the life. Okay, so the last time, so the last time, Proti spoke about the role of the photochemistry in the production of these bricks that are useful for building the life. And so you saw with him some preparation of nucleobases, sugars, because the last time in my lesson I showed you the so-called Formose reaction or Butler reaction, in which you have a simple compounds, formaldehyde and calcium hydroxide, that are able to produce many sugars in some complex autocatalytic reaction. But you have the variation with the light, so the photochemical reaction similar to that one. And you have seen also that the photochemistry can make some selection of the starting compounds. So some nucleobases, so actual nucleobases are quite stable with respect to other derivatives. Other nucleobase derivatives are quite stable for the photochemistry, so to the photodegradation. So it seems that also photochemistry could apply some role. So up to now, we are just seeing some clues, but we left something back because we spoke about the sugars. But as you know, so now we are so interested in the information during these last years. And so we are focusing on DNA and RNA. And so DNA, RNA, they are built, so they are stage compounds because they not only have nucleobases, they have sugars, but not commonly sugar. You have some ribose that is not common, and then you have phosphate, another element that is not common. It's too much common to find on the Earth. So then we have to see how they bind together. But the first case is that in the Formosa reaction, you form a lot of type of sugars. You start from C3, then you go to C4, C5, C6 sugars. So then you have aldols or ketos. You have a mixing together. Then at the end of the reaction, you have the formation also branches sugars and other more or less unknown polymers. And also the oxidation and the reduction of the sugar by them. So at the end, you have a mass reaction. But for sure, if you imagine that this reaction could have driven the origin of the life, you have to explain why the ribose is not the main component that you have in this mixture. So maybe the C6 sugars are more represented, at least for one part of the reaction. So we know that the sugar, if you leave an ambient temperature, the ribose is not stable molecule. If you leave, for example, at neutral pH, ambient temperature, you will have the formation of other isomers of the ribose. So not stable. Even this is a chemical equilibrium. So you have all this in the mixer. Also, if you take one of these, also you could have also the mixer. So they are. It means that the ribose alone in water is. If you left there, it's a mixture of these sugars in this amount. So it's quite strange that nature selected exactly the ribose. So how you can drive, maybe make some chemical selection, because as I told you, we can imagine that the Formosa reaction is like a living system, because you start from a formaldehyde, then you have the formation of sugars, then you have the decomposition. So the first one, we can say that the system is alive, and then at the end is died. So when it is alive, it's far from equilibrium, and so we can maybe make some selection. And how we can make some selection? So since we know that in chemistry you have some compounds, inorganic compounds, maybe easily available on the primeval Earth, that are borates and also silicates, that they can make some bonding to molecules. And they observed some years ago that if you make the reaction, and so this is the Formosa reaction, because if you remember, formaldehyde goes to the glycoaldehyde, the entire cycle is the main compound that is amplified by the autocatalytic cycle. And so this is the mechanism of this Formosa. If you add the boric acid, you will have a chain of reaction, and the end they give you a higher amount of ribose, because as you can see, it could be complexed by the boron atom, and so you drive the equilibrium toward this part, and so you avoid the decomposition of the ribose. Okay, so which is the importance of this reaction in the prebiotic environment? Actually, we don't know. Actually, we have no idea at all. But it is like a breakthrough, showing that in some case you can drive the selection of the compounds by using some simple compounds. So this is like a clue that it could be possible. So in the complex reaction network, like the Formosa reaction, you can move the equilibrium toward the part that you need. So do you have some questions?
Tipo, 2 o 3 giorni dopo seguo
Questions?
uno su Instagram che fa di questo.
Okay, let's go on. Um, Also, the other problem is that we have not free sugars, so we need to make some linkage with the phosphorus on one side, and the other side we have to make some linkage with the nucleobase. Also, this is not so easy. So the other hypothesis how you can synthesize the sugar phosphates, you can have if you add the simply phosphate into the Formose reaction, nothing happened. So nothing good happened. But if you use some other possible prebiotic compound that you can find, maybe this is almost unstable, but you have an idea that these compounds could be formed into the maybe with the irradiation of icy grains. And so it was shown many years ago that you can, with this way, link phosphate to the sugar. And so in this case, you already make this linkage, and this is useful for making other compound. And so as I told you, it's so strange for us that the life chose exactly the phosphorus for making these important molecules that we call the DNA and RNA. So many hypotheses are why the nature chosen phosphorus, but no idea at all. Even if you think you speak with chemists that they work with organic chemistry, phosphorus is not so used in the synthesis, so not maybe not so useful compound. So the idea is not so we don't know why there is this. But we know that the phosphorus is present in the so-called carbonaceous chondrites. If you remember when I spoke about meteorites, I told you that you have some kind of meteorites that are made mainly by carbon. That is like the icy grain that are cooked by the sun. So you cook with the photochemistry, with the heat, with the radiation, you cook the simple organic compounds to produce more complex compounds. So at the end, some carbon. And then when if you analyze this, you can find that they contain some phosphates, so calcium phosphates. So they are present in this material. So you can see here the type of minerals that you can find inside. And then the other problem is that calcium phosphate is not soluble in water. So this is the second problem. So as far as we know, so the mainly most of the phosphates are not water soluble. So the life need the water, but these compounds, these phosphates are not so soluble in water. Calcium is a common element. Also iron is common element that's present in the water. If you put phosphate, you will have the immediate precipitation, so the formation of the solid that is not soluble. But it is known that some materials, some minerals like this one, leads to a formation of some not so stable acids. So the hypophosphorus is not stable, but it's easily oxidable to phosphorus and phosphoric acid. So it makes some disproportion. Um, Also, you can have instead of phosphate, maybe you have phosphates. There is a big difference from the oxidation state of phosphorus. So one idea is that nowadays we have phosphates because we have a lot of oxygen in the environment. But if you are in the oxygen poor environment, the phosphates are maybe more represented, because nowadays if you take a phosphate, it's, as you can see here, some low oxidation state of phosphorus is immediately oxidized by phosphoric acid. But at the time there was no oxygen, so the atmosphere it was not oxidant, and so they could have played a role because they are more soluble than the corresponding phosphates. So maybe you have like so-called phosphonates, and then after the evolution, you have the formation of phosphates. But also this is an hypothesis because we cannot, in the first remember that we spoke about that in less than 1 billion years on the Earth, the life occurs. So, but because why we know? Because we saw some ancient like stones, and we know that inside there are some fossils that maybe there are some bacteria. But in any case, you cannot find inside any material, so you cannot find the DNA. So everything is lost after so many years. So another hypothesis is the phosphonate sugar. So in which the phosphorus is lacking of one oxygen. So usually the like phosphoric acid is like this one. It has an oxygen more with respect to this one, and here you have a linkage with the carbon to phosphorus. But this is not usual. So nowadays we haven't the linkage directly with carbon phosphorus, but we have carbon oxygen phosphorus. But in any case, if you bake in the lab, you produce this in the lab, yeah, you can have this compound, you can produce these compounds. These compounds is the chemical analog of this, that is the glyceraldehyde. That is the key compound of the, I don't know, go back. So it's the key compound of the foremost direction. So this is the autocatalyst. So we make the phosphonate chemically equivalent of this one. And with this, you can produce some chemistry that is similar to the reaction of, so the battle of a reaction. And at the end, you will have you see the nice linkages between carbon and phosphorus. So is this the beginning of everything? At the end, we don't know. At least we have another hypothesis, another chemical possibilities for the prebiotic chemistry origin of life. But now, let's just, so we spoke more or less about these building blocks of the life. But let's take so one step back. We see the chemical composition, so the elemental composition of these life building blocks, because they are so different. You know, so in the nucleobases you have nitrogen, in the sugars you haven't, yeah, only carbon, oxygen. So we can represent all the chemical compounds in this diagram. So we are neglecting sulfur compounds. In this diagram, in which we have carbon, oxygen, and nitrogen. So I'm not representing here hydrogen. If I have to put 4 elements, I need to make a tetrahedron. But in any case, this is, imagine that is projected on this plane. So for sure, some of the compounds, they can have more or less hydrogen, but now in this moment, we live like this. So here you see, if I have the sugars, all the sugars are also called carbohydrates, right? Because they are assimilable to this formula. And so it means that the ratio between carbon and oxygen is the same. So all the sugars, they stay on this black dot here. So only on this carbon, oxygen, no nitrogen, everything is at this ratio. So all the sugar that we know, they have the same elemental composition. Maybe if you have the oxidation sugar, you move a little bit toward oxygen. But in any case, with aldose and ketones, they have all the same elemental composition. So exactly one point on this diagram. So now maybe you are asking me, so what are these green dots? So these dots, they are dots representing the compounds of the Krebs cycle. Okay, so the cycle that is relevant to the metabolism, so the energy of the metabolism. And so you find only carbon, oxygen. Then you have nucleobases. Nucleobases, so the nucleobases, so I haven't here the formula, but nucleobases mainly carbon, nitrogen, and some oxygen somehow. And so you start with so the nucleobases are this white dotted, now they are becoming red. So this, and this. So you know we have 4 nucleobases, but in RNA you have a variation because you have uracil. Here, even if the quality of the image is bad, but more or less I represented, so I increased the size, and I represented the name because it's not possible to fit inside here. So this first dot is adenine. This second dot is the guanine, cytosine here. And then you have uracil and thymine. So this. So you see the nucleobases are on this line more or less. So a lot of carbon, nitrogen, very few oxygen. So, but they move horizontally in this position. Then we see the proteinogenic amino acids, because we have more amino acids, but only if you are proteinogenic, it means that they make the proteins and they are used by the construction of the proteins. And if you see, they are spread in this. So they are other dots that are represented in the other column. If you're curious, you can imagine to locate these names of the dots. So some of them are less rich in hydrogen, so more rich in carbon. That are this one, the compounds that are the aromatic one. So these are the aromatic, so they contain a benzene ring. So with the benzene ring, the amount of carbon is higher. So while seeing this, so I will now make you a question. So while seeing this diagram, so if I ask you, so do you think that all the compounds originated in the same environment? What do you think? Only by looking at the elemental composition. So let's open the discussion.
Maybe 2 origins?
Or maybe more, or we don't know exactly. But you see, at least you have some division of this. And also, if you think about the compounds originating this, that we know that present into the, for example, extraterrestrial environment like comets, icy grains, they are not compatible. So because these derive from formaldehyde, so sugar derive from formaldehyde, these derive from hydrogen cyanide because it has the exact ratio. So this is the exact ratio to produce this compound. The formaldehyde has the exact ratio to produce all the sugars. But if you mix together, you will destroy everything. So if you mix together, the formaldehyde reacts immediately with this. So they are not chemically compatible. So also we've seen that they are present in two different parts of the diagram. So maybe we have a co-evolution. We have a life based on this and based on this, or they derive from a different environment, then they mix later. Or maybe we are wrong. So simply the elemental composition varies and everything generated together. So we cannot imagine also this, but this diagram, so the position of these building blocks on this diagram let us to think that possibly there are different environments giving rise to this. And nowadays we can imagine that in the cell, and it's not homogeneous, as you know, because the internal of the cell has organelles, other parts. So you have the compartmentalization. You have compartments, and so the compartment separate the reaction. So for sure, you have because nowadays we speak all together because we made if you remember at the beginning, we are following the the reductionism idea. So we are breaking apart, taking in small pieces, small pieces. And in this, maybe we are losing the compartments. Maybe the compartmentalization you need at the early stage of life. Because as I told you, the chemistry of sugars and nucleobases, they are maybe not so compatible. Also, you have also some acidity, basicity, so different. So maybe the compatibilization occurs earlier in the origin of life. But now, so at the moment, we cannot reply to this question. So, but we spoke about the nucleobases. You saw, so Proti showed some of the synthesis of nucleobases, but concentrating on the photochemistry. But now show you that you see at the beginning of the study of the origin of life. If you remember, everything started with Miller. the 50s. Few years later, or made this reaction. So taking an inorganic compound, so ammonium cyanide, and if you take a solution of ammonium cyanide 1 molar, so greater than 1 molar, and you heat a little, you add some acid, but to get, you must be careful because you remember that the acid can release the cyanide, so it's so toxic compound, it's gaseous. So yeah, if you follow this, you are able not to die. You see, you synthesize exactly the adenine because here I told you the hydrogen cyanide, if you put in this diagram, is exactly on the adenine. So hydrogen cyanide is exactly on here. So it's like the adenine is like oligomer, so cyclic oligomer of hydrogen cyanide. And so we have many ways to synthesize that one. But then you need to have some oxygen also, because in order to have other nucleobases, you need somehow some oxygen. So where you can take the oxygen? Maybe from the water, maybe from another like cyanates. So cyanide with an oxygen, so as another known inorganic compound. So with this, you introduce oxygen, and by miracle, you have the synthesis of guanine, and okay, this is something in other compound, so still you have adenine before the introduction of oxygen. And so few years later or so, because now we are making a little bit the following more or less the timing of these discoveries. You see, some years later, they are able to also to produce other. So if you need, also we have some information. This compound also is a prebiotic. Remember, you can find this in the interstellar space. So if you mix this compound, use cyanogen, so all toxic compound, water, so you can have this. So you introduce some oxygen, and so you are able to make the synthesis of maybe uracil or cytosine. And you see that if you see the cytosine is not stable, and it's calculated that is in the conditions, so neutral pH, ambient temperature, it slowly convert to uracil. And so they are linked together. So there is some chemistry linking together this. So possibly imagine that you start with the uracil because it was available, because it can stay a lot of year into the environment. You start with the uracil. Then when the metabolism start to create compounds, you have an accumulation of this that has no time to convert to uracil. So maybe this is why we have different, so sometimes we have the uracil, sometimes we haven't. But it's all the other hypothesis that had. So again, Miller, after some years from its first experiment, also was able to, to produce some cytosine, starting from prebiotic compounds. So more or less, you mix the same things. You add, because for this, you synthesize the urea. It's also another compound that is a prebiotic. And you see, you can produce a cytosine. So Miller uses a trick because he started from the cytosine so that you can break down into this urea, tried several solutions, and then was able to make the synthesis. So years later, Saladino thought that everything started with this compound. And so with this, you are able to produce again the nucleobases. It uses some catalysts. So maybe here for the photochemics, for the prebiotic chemistry, we are seeing some use of some heterogeneous catalysts because it's also due to the variation in the thinking of people. So because you are a reductionist, first you think like Miller to mix just ammonia and methane, then wait. Then you think about, oh, maybe we have a planet. So in the planet we have rocks. So rocks contains minerals. Minerals are able to promote some catalysis. So that's why they added this also. So in any case, we found this. So I don't want to go in detail all the possible synthesis of nucleobases, but now we still have a problem. So we know that they are linked together. So in actual RNA, DNA, they are linked together. How we can link this together? I show you some chemistry is related to the nucleobases, other chemistry to the sugar. How we can link together? If you mix together, nothing happens for sure. So if you try, you can wait, but nothing happens. And also, now while speaking in today's lesson, you will also have an idea on how the ideas of prebiotic chemistry changed in all these years. Because what we are saying now is like the old prebiotic chemistry. So mix and see what's happened. Then actually we have a different approach, so more systematic approach for the origin of life. But in any case, we have this problem. So we have sugars, we have nucleobases, how we can link together. So let's wait some years. You see this Saturn. It found the way to put everything together. You see here it's using our glycoaldehyde, so was able to find, so we wish to add the chemistry derived from the Butler of reaction to the chemistry of cyanides. So by mixing these prebiotic compounds, he obtained this. So at the moment, we never detected these in the interstellar space, but we know that these could be present. So why not the all together? And then you see with some simple chemical reaction, you're able to obtain, you see what you need exactly. It's also in a quite good yield. It's so the reaction also, you have a photochemical step here. So this reaction, is it prebiotic? It isn't. So it's a matter of the content in which you're speaking, because he made this reaction by adding this reactant, not all together, not mixing all together. But in any case, it demonstrates a possible pathway in which you can produce a nucleoside by using simple chemical reaction, non-catalyzed, and also uses some UV light here, so the view photochemical step here to make the oxidation of this amino group. Because remember, the natural oxidation, it occurs in maybe 100 years. So he doesn't want to wait 100 years, so he used the photochemistry to use it. Also, he used some nice compound like the inorganic phosphate. So more or less, like a wizard made this, mixing all together, boiling together. But you can see some, at the end, you have one example, even if it's not, if you don't want to consider this as a prebiotic, you see a nice example of chemistry with the simple compound, no catalysis, no metals. So you obtain this in the 30% yield, not bad if you think about all the step, because it is the overall yield of the reaction. Okay, so let's take a few seconds to think about what you have seen up to now. So we are following the reductionist approach. So we break down everything, coming to the building blocks, and then we are thinking, now we have the building blocks, we are taking all together. But now I will show you a summary, because in this year I showed you only a few examples. But so not me, but someone made all the possible collection, the prebiotic chemistry. And you see, you are able to produce the amino acids by using all plausible compounds that are observed into the space. If you remember, one of the first I don't remember one, maybe the second lesson. I showed you like the 100 compounds found in the interstellar space, and you can find most of them. They are present in this list as a reactant. So these are plausible like a chemical reaction network, giving the well-known, for example, amino acids. And if you also think about nucleobases, here in this graph I represented all the possible pathway for the synthesis of the nucleobases. So the pathway, you see, they start here. They start from either cyanide, ammonia, so simple compound, water, and then you increase the complexity. Also, remember the Miller experiment. So the hydrogen cyanide could be made by making sparks inside the methane and ammonia. So yeah, we have some linkages. If this is relevant to the prebiotic environment, we don't know, but at least we know that we are able to produce the many interesting compounds by starting from small chemical compounds easily available. Most of them are inorganic, most of them simple, and most of them found into external environment. So don't want to spend too much, but if you remember, so we have many possible way to produce the amino acids. For example, this is for the spark discharge or irradiation, UV, X-ray, or shock heating, because also you can produce some shock wave into the reaction vessel. The shock wave usually are made by powerful lasers, creating a heating shock. And so, for example, this imagine when one object enters into the atmosphere. So by not only the heat, but you have the shock wave, you can make some chemistry. Hydrothermal synthesis. So we sometimes spoke about the hydrothermal synthesis. So what is the hydrothermal, if you remember, is the thermochemistry that is relevant to the high temperatures, so water, high temperature and pressure. And in this way, to high temperature and water, you have the dehydration of compounds. Also with hydrothermal synthesis, many of them, they use sulfur inside the reaction. And then you have to see here this number. They are the observation of the comets or in the space or in other environment. As you can see, more or less, they are all represented. Some amino acids, you have more possibility to find this. Other maybe less, so they are less easy to find. But I let you to know all this. Also, you can make the same for nucleobases. Again, a lot of conditions, a lot of people working these years. Okay, they are represented. You can produce this in different way by UV radiation. You see, where you use the spark discharge. A lot of possible high temperature, low temperature, very low temperature. Okay, very high temperature. So you can imagine. So with or without catalyst. So in any case, many possible pathway to produce this continuum. I don't want to go on in detail. Here, this graph is only to show you how they are linked together. But at the end, so we have monomers, but how we can make polymers? So because now we are following the reduction approach. So hopefully I convinced you that we are able to produce in a easy way. So nowadays you can say the cheap way, because usually if you make some chemistry with palladium, maybe you spend a lot. This is just chemistry they can make in the pot. Okay, they're toxic compound, but in any case, so easy to find to produce. But then what you will do with this? So how you mix? You can make some polymerization. So we have some reply. So with amino acids. Okay, the first is, okay, you boil everything, you fry everything, you will have a polymerization. This is okay for the amino acids that are the higher thermostable compound. If you cook the sugars, you know exactly what you will obtain. And if you cook nucleobases, again, you have the decomposition. But amino acids, they are quite strong, so why heat resistant? So if you heat, maybe you produce some polymer, but you have some degradation. So we are not interested in this chemistry. But you have a milder chemistry if you use some sulfur, as I told you. This anhydride, this is the carbon dioxide with one sulfur instead of the carbon, of the oxygen, sorry. And so with this, you can activate because if you are a chemist, you know if it's not reactive, you need some activation. Usually chemists, how they activate this? They activate maybe this part, or they protect this, they make some chemistry, no, but it is easier. You produce this, it's like a thiocarbamate. Thiocarbamate is not so stable. And so not so stable means that they can react. So by using different reaction and so on, you can obtain some dipeptides. And then by repeating the cycle, so you pass by this step, so by cyclic derivative, this is the key intermediate. And then this could give you some maybe oligopeptides or purines. So this is another hypothesis. So shown in the laboratory, so you are able to make some chemistry. Also, you can see you can produce a nucleoside. Again, the role of sulfur and maybe the role of hydrothermal conditions. But now, so we need to make some summing. So now we have some reaction, scattered reaction, some clues, some possibility, but in any case, we are in the primary step. So the problem of the approach of the reductioning is that when you reduce something in an easier way, you don't know when you stop, when you lose. The problem is that at one time you will lose some information, some crucial information. And when you go back without that information, that we can also call the entropy, you cannot go further. So you will step somewhere, we stuck somewhere. So we have the RNA world hypothesis because so a living system, you know, is linked. So an egg give you a chicken make eggs again. So they are in the cycle. So this is a question of who was first, the egg or the chicken? So how you can reply to this question? So it's difficult to reply, maybe impossible. So what do you think? Okay, maybe you have one intermediate that is an egg and a chicken. Okay, if you make a chicken egg in one part, so one derivative that is both the chicken and the egg, maybe you solve the problem. So this is another possibility of the reductionism. So you have two objects, A and B. You combine them, making one object that has only what you need of object data and object what I'm speaking. So in the 1989, these two guys obtained the Nobel Prize because they found that you know, nowadays we have enzymes. These enzymes are made by amino acids. So they found that you have some enzymes that are made only by RNA. So we found the chicken and the egg together. So we closed the loop because the RNA, so we know because nowadays we are seeing these some so-called ribozymes. So we have some enzymes made only by RNA. And we have some enzymes made by the two parts. So at one of the, so this Gilbert in 1986, he talked about, so for the first time, he spoke about the RNA world hypothesis. So imagine like this. So now we have ribozymes together with we call the normal enzymes. And this guy thought, okay, maybe we have the ribozymes because they are the remnant of the one ancient living organism. So this organism was made only by RNA. Then the amino acids comes. So the amino acids are better to make the enzymes, but you need some translation apparatus. So this evolved later. And so we can start from thinking only about RNA. So another reductionism. So this up to now is one of the hypotheses that is taken more into consideration, at least up to some years ago. So by summing up, nowadays we have the DNA, RNA, and proteins. So we can divide these into information and catalysis. So proteins, maybe they are good only in catalysis. DNA maybe is good only information. RNA is in the middle because we have some ribozymes. And so that's why we choose this. And so the idea is from RNA, you will originate the DNA, the proteins. Then we see this is strange for what we know, because if we think about the maybe you told you we spoke about the comets, interstellar space, so we find the amino acids into the they are easy to find into meteorites and the extraterrestrial bodies. Less easy to find some nucleobases, so they are less common than this. But maybe some people think, okay, you found amino acid because they are more stable. Okay, so but we think we follow this hypothesis. So this hypothesis is like we think about our personal computer. So the DNA is like for the long storage, so like the hard drive or our computer. The RNA is like the RAM, so the volatile memory that we use and you throw away. And all the rest of the catalysis is due to the rest of the hardware, so microprocessor and so on. And so more or less this idea also, that's why it took place because it's the beginning of the thinking of computers. So the computer can have some cross-fertilization to the idea of the RNA, because we are separating information from the catalysis. So one of the scientists that started to work practically on this hypothesis was Leslie Orgel. And now we saw this hypothesis. So we started from some like nucleosides. Then these nucleosides make some oligomers. And then you can see they make some polymerization, and they can make some hydrolysis. So with the polymerization, you polymerize, with the hydrolysis, you go back. So you are not losing anything. So yeah, it's not thinking that you can have some degradation. So the degradation is neglected. So we don't think about the degradation. So we have association, dissociation, association, dissociation. Then sometimes you will have that some oligomers can stuck together. If they make some base pairing, they are more resistant to the hydrolysis because you have another kind of interaction. So they polymerize, they stuck together here, they block in this position, because for the hydrolysis you have to separate and then make the hydrolyzation. So they are more resistant than the hydrolysis. The unpaired one, they are easily hydrolyzable. So this grows in the complexity up to they reach a point in which they are able to do something. The problem is that in order to make some catalysis, you need a little bit more complexity than 2 or 3 only nucleobases. So this is a cycle. So you have polymerization, you have the hydrolysis, and so you need to have 2 stages. So the stage A, the stage B, and at least they are 2 different conditions. But in any case, so imagine you have monomers here. So now we are speaking about the energy, so the stability. The monomers are here, the polymers is there. So going down is easy, the step A is easy, but the step B, if you go there, you need some energy for sure. So it's sometimes written that we have, so we need some energy somehow. So this is, I don't know why it's not in the animation. In any case, this is not sufficient to have this. So these oligomers, no, they show no catalytic effect. In order to have a catalytic effect, you need that make some, they have some shape. So some part they make some interaction, other part maybe they are more free. And so if you think to add another compound that it could be, so at the moment we don't know exactly, it could be another maybe small amount of like peptide, or can be I don't know, some part of some compound related to metabolism. But if you have some shape interaction, maybe the compound, so the RNA that is able to link in some way, it interacts more, and so it is more resistant to the hydrolysis. So again, you see the interaction with something, they make some hydrolysis resistance. So when you have the degradation, you degrade all the others, but this can survive. Then this may be how they can replicate, we don't know exactly, so we have no idea. So, but so we have the polymerization, but in order to have some catalysis, you need at least 20, 30, 50 nucleobases, and you need something like that. So you need the formation of these loops. And because the catalytic activity usually is made by these loops on the other parts that are not linked. So this block give you the structure, give you the stability. These give you the reactivity. So stability, reactivity. So without this, you haven't this. But if you want to think about the duplication of this, now there's the duplication of this, so we use enzymes that are present in the organism. But if you need at least to duplicate, you need to break these bonds. Okay, something is good because this bond usually are weaker. Usually means that it depends on the conditions, because if you have many, maybe you're not able to hydrolyze. So if not so many, maybe you are able to make some hydrolysis. So for sure, this is more stable, because usually it goes like this. So this automatically makes some self-detection and closes into a loop. So you need some increase of energy. Then when you stay in this unstable state, because it's less stable, you should have some base pairing, so there's some recognition, and some polymerization. Also this, you have two steps. So we are thinking about how it is critical, this approach. So you need some energy, not too much, because you don't want to break down. You need some base pairing, you need some polymerization. So the reaction must occur here, not here. And then you have to make a separation. Again, you need energy. Then you have the folding, and again back. So in this cycle, you can have a self-replication at the end. But the folding is spontaneous. You need the energy. But now we are not thinking about the method. So where is the metabolism? So something is not working, like this plug. So we have parts, but they are not speaking together, because now we neglected it, because with our reductionism approach, we neglected the metabolism. But now we need the metabolism, because without the metabolism, we have the energy. Maybe we have some cycle in the, like the sunlight, in the freeze-thaw cycle, some evaporation. But still, some part is missing. So something, this object is broken somewhere. So the beginning, so Orgel thought that okay, so you're right. Maybe you need by chance that this interaction give you something that is useful for the formation of some superior function, like the catalysis. But in any case, no demonstration of this, and this is a difficult step for sure to imagine. Okay, but let's go closer to our ears. And so the problem is at the end, so you need some RNA that is able to catalyze the replication. So they in the laboratory, they try to find some polymerization, And so what they are doing, they are searching some simple compounds that are able to recognize and to make some primer template. So they wish to make some study this step. So they are able to make a template and make some catalysis, some self-catalysis. So this approach was conducted into an approach that is like the evolution. So you have some selection, manual selection, and then you select the fit test, you make some variation in the code, and again you make several cycles. You see at the round number 18, so each round is a cycle. So you start to synthesize this, you made variation, you made the best fitting, and then you obtain one compound that is able to make some templates, so to drive some template synthesis of itself. And so this is so you will obtain at the end the autocatalysis. So wait some years later, Joyce found because the problem is when they step from one to another one, in order to make this, they made the de novo synthesis starting from the DNA. So they are not working like in the prebiotic chemistry. Here, there is all the biology that you need to make the variation, so the manipulation of the genetic code. So the idea of this is, okay, we need to produce. So I want to produce one RNA polymerase made only by RNA. And so if this is possible, we can have a clue that we are able to make, so to drive some reaction in the prebiotic environment with only RNA. And so with a complex approach, they were able to synthesize this. And so this cannot replicate itself because it's a quite complex molecule. But they found this polymerase then can replicate nucleic acids. And it can replicate for some of them. So 10,000 times the what you get with other compounds. So because usually when you perform this, the PCR, normally you're using enzymes made by proteins. This is a catalyst made only by RNA, and it's all artificial. So this is not present in nature. So they invented something, they reproduced this something in the nature. How they done? Nobody is able to make calculation, maybe to think about from this theoretical point of view, how the structure should be made. So they started from some idea. They base some Darwinian evolution. So again, so they replicate the genetic code, and then they choose the best. The best was sequenced, and again they make some modifications, selecting, up you can arrive to some part. And so, but at this time, so this is an important key step for the RNA world. So you have seen how many years from the beginning of the idea to the formation of something that is more similar to what you can exactly happen in the RNA. But still, so the import is a very big thing that you made, that they made, but it's not able to catalyze the formation of itself. How it is made? So they follow a lot of different. So this is the structure of the RNA polymerase. So the ribozyme. So they make some steps that you can do only in the laboratory. So this is not related completely to the prebiotic environment, but still is important. So how would they do? They make they add a primer, and this V is a photo linkable. So you can remove this linkage by using photons. So you have a primer that is a sequence. You have into natural DNA, RNA. So you have a sequence that is the starting sequence. So the recognizing sequence that you have to build something. So you add the RNA that you need to replicate. This RNA should contain the counterpart of the primer. So that must have a part that is complementary to the primer. If not, not possible to do. Then you have here the attachment of the nucleobases. At the end, you have the polymerization. Then how we can know is because now you wish to choose which one made the best polymerization. How we can do it? So that you use some substrate that contains a molecule that you're able to attach to the RNA that you synthesized new. So when you you remove this by using photons, you have the release of this sequence, and then you know that if it worked or not. Okay, so imagine to repeat this in the several test tubes. So 1, 2, 3, 1,000, and then so for each one you you put some RNA like this with some modification. Then you see that in test tube number 1 you have some of the recognizing. The test number 2, no. Test tube number 3, maybe. The test. Then you know what they do. You take the test tube working. They analyze the sequence, and from the DNA, they produce again another part of RNA. Okay, so they make some modification again with some approach. So that's why this part is. Because it's not related to the prebiotic. So this is a reverse translation and PCR amplification. So one thing that could happen only in the laboratory. But in any case, this is an approach that could be used also for the production of many compounds. I'm telling you that, okay, this is the sequence. Okay, if you're curious, I will send you the link because now I draw something in the top, because here you have the exact sequence of this magical ribosome. And so this is like an evolution. So this is more related to the modern thinking of origins of life, because this you can making an artificial evolution of the compound toward the direction that you choose. So you are making some artificial selection. And this is the important topic that also is used not only in the prebiotic chemistry, but for the preparation of many catalysts and the preparation of maybe new frontiers of the chemistry, also not related to the prebiotic, because in this way you are able to produce maybe a better catalyst or a better compound or some drug or some structure by using this in vitro artificial evolution. Okay, so I stressed you a lot. Do you have any question?
Thank you very much.
Yes, actually, I have a curiosity.
Yeah.
About well, in the first part of the talk, at a certain point you said we don't know why phosphorus was somehow selected for this.
Yes.
So it could be that it somehow contributed to the linkage of sugars with nucleotides.
Yes, because you so since we don't know anything, it could be that it's the only compound that is able to do this. But why? So the problem of the prebiotic phosphorus is exactly like this. So we live in the water, and the phosphates usually is not soluble. And maybe you're right, because if you think, okay, if it's not soluble, if it's stuck on bottom part
Yeah.
of something. And if the RNA, DNA stays here, so you can have some concentration of this. This could be an hypothesis also. Yes, maybe also the less solubility of these compounds or the function. So by chance, because I like your approach, because now we are thinking from the reductioning point of view. Even the RNA world is debated because it comes from the reductioning approach. We start from the simple compounds able to make everything.
Yeah.
So maybe the phosphorus made the same. So it was the only able to produce these linkages, giving the origin of the RNA and DNA like we know.
Okay.
But I will show you. So since you made this question, you will get other some 6 slides. So because then I will end. I don't want to. Okay. We'll do fast. So you, because this phosphorus is not good for many reasons. Maybe you're right. Maybe no. We don't know. But what we know exactly. So now there is the post-RNA. What is the post-RNA world theory? Are you a chemist?
No, I'm a molecular biologist.
Okay, so a chemist can tell you this thing. You have this information on polymer. Now we spoke, okay, ribozymes can do catalysis. Amino acids, so like proteins, can do catalysis. But the chemist told you, if you have monomers, they are sufficiently different, and you are able to link in the correct way. If they are sufficiently chemically different, you can make some enzyme, so like some catalysts. And these are called the molecular imprinted polymers. So for a chemist, if you start from one monomer or another monomer, it is not worth much. So it's not so important. It's important that for each chemistry, you have a sufficient variation of compounds. If you have sufficient variation, you can have the catalysis. But okay, as far as we know, the only so the easiest and the prebiotic object that are able to make some interaction between one to adenine with the thymine, so they are a nucleobases. So we don't know many other compounds. But now we are debating on the post-RNA. So what is the meaning of post-RNA? That maybe you have not exactly RNA. You need some informational polymer here. If you're able to create an informational polymer, also if it's not exactly RNA, it is not so important. Nowadays we use RNA, DNA because as a biologist, it's so easy. So I give you one molecule of DNA. The day after I have one mole of DNA more or less, because with the PCR you can amplify a lot. So we have a lot of machinery in this. If I give you a molecular imprinted polymer, like a synthetic one, how you can make the duplication? It's almost impossible. But what we learned from this, the approach is important. So maybe we can follow the same approach, not starting with the nucleoside, but something similar. So the nucleoside are the sugar. So Schmoser thought, okay, why ribose? Maybe we can produce some like homologous of DNA without the ribose. We substitute ribose with something other, with some other sugars. Also, you can substitute. Also, we can with also non-sugars compounds that are not like this one. You have cyclohexane, so far from sugar, but you search something that is able to give more or less a three-dimensional structure and the size of the sugar. So you produced several possible analogs of DNA and RNA. So they called XNA because X stands for xeno, so something that is not the basis. So you see, this is so before you can make some enantiomers, but I don't speak about enantiomers now. But you can modify the deoxyribose you see they can put arabinose, fluorarabinose, triose, or some other analogous, cyclohexene, and some other compound. Also, you can make some change in the nucleobases. And so you obtain many of possible compounds that are able to act as DNA. So they can make some base pairing. They will make some nice folding, like the DNA, so the double helix folding. And also, Nielsen talked about some protein derived compounds. So you see the backbone here is the protein, and here you have the nucleobases. So the protein nucleobasic acids. And what is the most strange is that some of these compounds, some PNA and some of these XNA, they are able to make base pairing with the RNA and normal DNA. So they have the same structure, 3D structure. So they make a base pairing. Some of them make the base pairing that is stronger, some that is weaker, and some of less hydrolyzable, more hydrolyzable. So we have a different variation. And also this gives rise to a new frontier in the chemistry, in the treatment also, if you want. Because you can use, so imagine nowadays we are making vaccine with RNA, so everybody's speaking about this. And also you can use some RNA to block some unwanted function. But then the RNA is quickly hydrolyzed. But if you imagine that you're able to synthesize an analogous of RNA that's not hydrolyzable, what do we see? We are making, maybe imagining another kind of a medicine. And this is related, so they started from the idea of the prebiotic chemistry. And also, I told you, you can use, so you can have linkages between XNA and RNA DNA. But also, what is this guy, so Krishnamurti, showed that, okay, you have base pairing. By even, you can have some mixing. So you imagine to break everything. And you produce one XNA that has one part that is maybe, you see, derived from one ribose. Then you have another compound. Still, you have one possible homologous that is able to make the base pairing. So in line of principle is able to make catalysis, because you can make, if I produce this, the same sequence of RNA, I can make catalysis also. Maybe this is quite strong, because if I use usually peptide bond is so strong. So maybe if I transfer a ribozyme, I'm able to copy this to make the PNA. I will obtain maybe the same catalytic efficiency, but the chemical resistance is far higher with that one. So you can use in the harsher environment maybe for making new chemistry. And so you see the phosphorus is important in most of them. Some of them is not necessary. And so what I'm telling you is the base pairing is important. Maybe the backbone could be different. Also, we don't know nowadays if the choice that is driven from the functioning, for the functionality, or from some coevolution, or the result of many selections. Okay, now I think we can finish here, because I filled your heads with a lot of information. I hope that I told something useful for you, something new for you that is able to maybe lead you to think more about of the box. So do you have questions? Are you alive?
Yes, no questions here. Okay.
Yes, and thank you for the answer before.
Okay, you're welcome. Okay, so next question here from Paolo. So he's asking if I think, so me, if I think if it originated before the metabolism or replication. It is actually a good question. So I told you I'm a chemist. So chemists, they like more the metabolism. But so many of chemists think that metabolism first. Many biologists think replication first. Many physicists think you have the panspermia. But I think that the reductionism approach is wrong. So maybe at the beginning you have something that is not assimilable to only metabolism or replication. Maybe you had some critical step that has all together. So that's why at the moment it's difficult to think about this, because it's difficult to find the good so mixing metabolism and the replication, for example, or self-catalysis. But maybe this is a crucial step. And probably we are not finding this because in the reduction approach, you think only A or only B. Maybe is AB. So this is the actual thinking of the prebiotic, so the origin of life scientists. So they think that maybe the reduction is wrong because I don't know if you remember also the Merli thought at the beginning, the first lesson about the reductionism, because many people, so many scientists think that we all originated from some last unknown common ancestor, so Luca. And how they know this? Because they analyze the DNA of the possible living organisms that they know, and they found some similarities. And so giving back in the time, so you can build a tree of similarity also by using simple programs. And what you get at the end, at one end, you will attain only one organism. But imagine that you have more than one organism in the beginning. If you make this approach is reductionist, so even if you have maybe 100 organisms at the beginning, with this approach, by seeing the differences and analogies in the DNA, you will find always one, because the reduction give you the one. So nowadays, people thinking that Luca is not one, so it's not a Luca. They call Lucas with the plural, because they think about the modern biology. If you have the survival of life, it is because you have some differentiation. So if all men or I don't know, plants, maybe not good. So you need to have some variation. Better to have some genetic differences, because now the problem, we are so many, so we are losing the difference, the bio difference, and this is a big problem for the future of the life. So why is not in the past? It should be the same, I think. So you cannot have only one, but you have to be a pool of organisms living together. And so, by replying to a question, I think you have to have something that is that mixed of all the parts. So something is called an irreducible complex. So irreducible complex.